Assalamu alaikum everybody, welcome to the first tutorial of CSE340 except the introduction. So today we'll be starting with review of DLD, Digital Logic Design. That's the primary thing that we do in CSE340 computer architecture. And DLD is nothing but CSE260 Digital Logic Design. If you have done that, then that's DLD, Digital Logic Design, and we are going to review those stuff because we'll need them here. And also I'll be going to the DLD part very quickly because we're not going to spend time on that because you already did that you did a whole course about that, and there are some extra things that have been added and we'll focus on those things. So the truth table, AND gate, OR gate, NOT gate, you already know this. I'm showing you just because, for the sake of revision, just in case you forgot, NAND, which is the opposite of AND, NOR, which is the opposite of OR, an exclusive XOR, and it has its own XNOR, which works with these values when they're different and when they're same. And Boolean functions are based on 2. You can have 2 to the power 1 to something, no matter what it is 2 to the power something. And of course there are the Boolean laws of Boolean algebra. You did this in CSE260 and you kinda did this in CSE230 as well, discrete mathematics and digital logic design. So just pause the video and look them up if you need a review. They're easy, so that's all. Okay, now we are getting into some critical revision because you'll need this. I'll just spend some time over here. This thing over here, you can guess what it is. It is a sum of products. Now some of you have problems understanding that. If you don't, great. But if you have problems, sum of product is simply what it sounds like, sum of two products or more. So you have P1 which is a product 1 and P2 which is product 2, and if you add them, then that's literally S.O.P, sum of products. That's all it is. So to find this Y, you'll have to find out A, B, C, and then you have to do an AND with the values of this S.O.P, and then finally you will get maybe 0 something, something, I don't know, I didn't do that. So that's how it works. Now what's next? Ta-da, guys, here is the solution. Now as you can see, they have solved it out. Now this is a good revision. I'll take my time over here as well. So we are supposed to find out Y, not Y, this letter Y. So A, B, C, we have an expression over here. We have this, note this one also, and we have this whole thing. Now an ingenious idea would be to find out A, B, C, and some of you will go out of your way to find A naught, B naught, C naught, which is great, but it is not so great because sometimes it will cause confusions. If you just use your head to do naught of A, B, C, then you will be avoiding a lot of mistakes, especially if you're under pressure and you have a huge equation. So it's a good idea to do ABC first, and when you have done this, and as you can notice that there are 4 zeros, 4 1, I'm pretending that you kind of forgot 260, so I'm taking my time explaining it. Some of you are like, oh, you know this stuff, what does he think, guys? You can just skip the video up to like 5 minutes, if you're offended, but let me do it. And you have 2 2 2 2 and then finally 1 1 1 1. The objective is to get an expression out of all of these three, which is 2 to the power 3, and then you have A, B, C. We don't do this one at once. We deal with A, B, A dot, B dot, C first, and then we knot them out. So we got this part done. And then, okay, let me change my colors. Okay, and then after, so we have to do this part. So an ingenious idea would be to deal with this and this separately. So we did that. And now you can add them. Okay, now we know what Y is. Y is the AND of this one and this one. So if you AND out these two, and what is it talking about AND out? AND means, AND gate out these two, that means 1 and 0. No, The only time it will be true is for 1 and 1, and as you can see, that's the case. 1 and 1 gives you 1. 1 and 1 again gives you 1. So your solution is actually A when it's 1, B when it's 0, C when it's 1. A when it's 1, B when it's 1, C when it's 0. Now that's an easy way to explain this, but how do I write that? Okay, let's see. Remember I told you A when it's 1, B when it's not 0. When it's not 0, you tell it as not. Look, somebody is knocking me on the messenger. For moving on. So we have 3 variables A, B, C. We can have up to 2 to the power. I already told you this stuff, so I hope you understand this part. I'll tell you again in case you didn't notice. A was 1, B was 0, and C was 1. And A was also 1 in the second one, B was 1, and C was 0. Let me show you. Over here, look over here. How do we get Y? This is very important because you will have this in your quiz. You all probably had one, but you will also have it in your mids and in the finals. We have to find out the conditions where these two gives us true, which is Y. And so that the case is this and the one below. Now this is the part where we focus. Okay, A is 1 in both cases, B is 0 in one case, C is 1, and vice versa. That's the thing we just did over here, and you can tell me what it is. Let me tell you what it is. It's a sum of a product, another product, so it's sum of products. I took my time over here. Anyways, even though you did this one in 260 as well. And here's another thing you can see, and we can use this sum of products and we'll get another thing, but let's just go with the flow. Okay, this thing is very annoying. Okay, if you're happy showing the main toolbar, then just do that, but don't keep showing up like that. Anyways, so you have this one, another Y expression with 5 variables. Now isn't that something? Let's see, what did they do out of this one? So this is the function. Let me get my pen out of there and I'll show you something over here. This is sum and sum of a product, of another product, another product. So in case you're wondering, these are the Boolean laws we used. I showed some to you a few minutes ago, and when you use them, what is this expression looking like? Sum product, sum product. Isn't this a product of sums? When you have a S and S and an S again, and these two are a product of sums S1 and S2, and then again the whole is a product of S1, S2 and S3, and that is why it is called product of sums. I don't even know what I'm drawing, but just imagine them, which is known as P.O.S. You did this one as well. Anyways, so how to write Z as product of sums in the same way, but as you can see, this time it is product of sums, and this would be sum of products. If you use the Boolean laws, you will get the product sums out of it, and that would be Z, and Z naught is the sum of products. Okay, it's interesting that if you just reverse the sum of products, you will get the product of sums. Isn't that something? Anyways, moving on. And here is another demonstration. A naught, that means this is sum of products. To get P.O.S, you have to not out this one. That means you have to put the not. That would be 0 0 0 0 1 1 1 1. This is not P.O.S. I'm just saying, just in case you have to do. This is a function, and they're demonstrating how you do that. So as you can see, I showed you before that you do this part first, and some of you will see B naught and A naught and try to make an A naught, B naught, C naught. It's not necessary. And we did A naught over here just for the sake of, you know, simplicity maybe, but it's better to use this and not this out, because that will keep you away from confusions. And so when you have these two expressions, you find the y. Anyways, enough of this product of sums and sum of products. Let's move on to the next thing. And you remember don't cares, and they will be given in the question, and it probably doesn't use, you won't find that. This is not necessary as well. This is, you can read them out if you want, but we're going to skip those things. But we do need to know what a transistor is. Transistor in computer, it's controlled by current. It's a thing that is used, and why is it used? We'll be going through that in a very short time. Using transistors and resistors, one can build circuits that are okay. We know that already. Now this is a law. Just know and remember this. Gordon Moore, someone who's the founder of Intel, said one thing: number of transistor per mm square doubles every 2 years, and some of them actually it is still proved true till now, and I don't know if it will be maintained until the end. Logic gates. Now it's time to get into drawing and artwork. All the things we did for now were maths, equations. Now it's the real deal. Now it's with the arts. So all those things we did, these are the figures and or not, and you already know these. So we're going to skip ahead these things as well. Logic gates, NAND, NOR. These are for the sake of revisions. These notes are available in the 340 folder, so you can just check them out. I'll go to, and this is okay, let me spend some time over here. Some of you face problems with this. How do I draw a logic diagram? You have what if this was a table, you know, truth table? You would have found A, B, C first, and then you would find this separately and this separately, and then you would add them and get a y out of it, right? Same thing over here. So let's deal with this part first. A and B. So A and B is fine. What the gate they're using, AND. So I have an AND gate, but they're knotted out. You know, it's a NOT version of that. So we use a NAND gate. So we did this part, okay? Don't focus on this for now. First, and then we do this part, A and C. So we have A already, and we have C. Then put it on an AND gate. We did this part. This part is done and this part is done. Now we have to do an OR of these two. So take an OR gate, and then you will get Y. Simple as that. So that's a logic diagram for you, and this is a more complicated one. So you can have NOT gates and bring. I'll show you. I don't know why didn't they do this. Oh, they did do this. See, you can take 2 from A. You can just take something like this and something like this, and this one will have a NOT gate. Okay, so one is a normal A and this one is A naught. In this way you can do the same thing for B, for C, and then these things will be easier for you. So first we find out A naught but B is normal. So A naught, this one, and B is normal, that means this one, and take them on an AND gate. Okay, did this. Now we focus on this one. This time A is okay but B is not. So A is normal, this one is normal one, and B not, this is, oh, they did do this. Okay, done. We did this part as well. Now OR them out. So we get OR gate and put the results. I think that was a good revision for your logic diagram, and you remember this guy probably took some marks away from you when you were doing CSE340. This guy is a multiplexer, and he needs an extra input of S, which will actually send a 0 or a 1 depending on what the control unit or you yourself give it to it. So that S would, if it's 0, then you will get a result, and if it's 1, you will get a separate result. As you can see, if you send 0 from here, it will be 1, and 0 from here, it will be 0. But if you send 1 from here, it will be 0, and this will be 1. So the result will change, and you will get two types of result depending on what you send. So that's a multiplexer for you. It is also called a selector. You will select what you will send and how you want your results. This is a more detailed version of that. You did all of this in CSE340, so I'm not spending my time on this one. I'll leave it to you for your revision. Okay, now we got ourselves an interesting thing. Read only memory. See out the title because I have to zoom it down. Okay. Now we're talking about memories, and you already did this one as well, so this is not so important. This one is important. Programmable logic array, PLA. You will find this a lot in your 340 course, and we'll know about this. The important thing about this is actually how you draw this. So we'll get to that. This is a very simple version. Nobody will tell you to draw this, believe me. But the one thing you need to draw is this one. Now you will say, okay, this is a very simple diagram. Why is it simple? Because you find a dot b, you find the required variables, and then you just find out the y's. That's easy. Notice one thing. In the previous diagrams, we did something like this. When we required, we only did what we needed to do. So the A had this, and this, suppose we have a knot over here, and then B is normal, we don't even need a knot, and A takes an AND gate, B takes an AND gate, and then this A knot takes an AND gate, B takes another, and then these two AND gates get into a, I don't even know what I'm drawing right now, another AND gate. Please pretend that these are gates because they do nothing like a gate. They look like a, you know, an octopus or something. Anyways, so we didn't draw like something that if you want to add another AND gate over here, you know, like this, then you'll have to pull wires from this and from this. You know, that's a problem. But unlike this one, this is such a circuit that no matter how many you want to add, you can easily add them. I'll show you how. For example, you want to add another, you have two gates over here, two OR gates, but you want to add a third one. Do you have to make any changes over here? No. What you need to do is just take a pen, you know, draw the gate over here, make your own Y3 based on something. For example, we will make something Y3 like, okay, let me just do some real engineering stuff right now. Yeah, A, B star, which is this one, plus ABC. Anyways, so you have these two, okay? So this one and this one. So we have 1, 2, and 3. All you need to do is pull this out, take one from here. I need to change the colors. Black it is. Take one from here, from this gate, and I need this gate as well, so I'll have to take one from here as well. Okay, I'm done. I don't need anything in the third one, so with these two I'm fine. And so I have my Y3. I didn't have to draw A again, B again, C again. I just took some extra wires and connected them with the circuit which is already available for connection. And you know, based on, even if you want to add another gate over here, something like B not A, C something, you'll just, you know, extend these and create them. You don't have to draw A, B, C again. That's the concept of PLA. No matter, whenever you want, you can design it. You get programmable logic. You see? So you have to draw PLA like this. If you draw PLA like a normal logic diagram, then you'll get a 0, especially if you're in Amitabh Sir's section, you'll get a 0. Anyways, okay, this is the explanation that I just gave you. We are done with the first part. Now we'll go to note 2. Okay, so we have subtraction. Now subtraction, you have done this, so we're going, and now one thing I want you to note about subtraction though is simply it's just the not of this. So if it's actually x minus y, as a programmer you would think like x minus y is actually x plus y naught. So if you add that, then you're done. You're doing x plus y, x minus y, sorry. Okay, that's the only thing you need to know from this. And B invert over here, some of you have faced problems with this. B invert is nothing but it will send you the inverse of B. So if you have 0 over here, B invert will send you 1. And how do you use this? We'll see that. Okay, as you can see over here, this is a ripple ladder or something, but whatever it is, let's just focus on the B invert. What this guy is doing over here is the invert of B. So if you set 0 over here, he's sending 1, 2, 1, 1, 1. And this guy is sending B0, B1, B, whatever. You see? He's doing the work of B naught. And this is sum, and this is carry, and this is actually a ripple adder. You have to remember that name, ripple adder. R-I-P-P-L-E. Why am I writing this? You will see that anyway within a very short time. As you can see. Okay, so this is a ripple adder. Sometimes it will cause overflow. You don't have to talk about that, it's not necessary, but there is a faster way to do this. Now why do we need a faster way? Why do we need a faster way? Before you know what is the faster way, we need to know why we need a faster way. Let's do some architecture stuff now. You see, how will this circuit work? This one, all of these are operations. You can say O1, O2 and O3. Now O3 and O2 cannot work. Why can't they work? Because this input is dependent on this operation 1. And O3 is even worse. He needs to wait for operation 1 to complete first, and then operation 2 to be completed first, and then this old poor old guy will get an input. Maybe if the work is done in 2, he will not get any input. So this dependency on each operation, so if you have like thousands, then the 1000th operation O1000 will have to wait for 9 operations to work, which is like very frustrating. Even though it doesn't have a life, it is frustrating us because he doesn't care, but we do care. We can't watch 999 operations go. So we need to find a faster way. Now what's the way? This is an option. How do we do this? We divided them into 2 parts. So this part contains half of it. If it's 32-bit, if we are dealing with 32-bit, 16 operations are done over here, and the rest of the 16 are done separately. So if n is equal to 32, you will need n by 2 times to complete. This is n by 2 times faster. And as you can know, the mux, what it does, you already know that it takes a B invert and gives you a final S or sum, whatever you call it. So that's this part, and this is faster. It is n by 2 faster, remember that. Now there is one thing called arithmetic logic unit. This looks so easy. It's such a simple diagram, isn't it? But I showed what's the original story behind this in the last slide, so that's how it is. So that's the advantage of ALU, and we will use ALU to do operations very, very quickly. Now moving on. Okay, speaking of adders, we need to know about half adders. So let's see half adder. We got a little too advanced a few minutes ago, so we'll try to slow it down a little and start from the basics. You remember half adder, right? It's a 260 stuff. I'll just show you. S is, as you can see, an XOR gate, this one, and A is an AND gate operation, so this will give you a half adder work. And half adders together can give you a full adder. And this full adder is actually the use we are doing in our ripple adder I told you before. See, it's a ripple adder, but the problem, I explained everything. Let's just see the part, you know. This n equal to 32 will take a long time. I told you that already. And there could be an overflow as well. So encoder, you remember encoders, but you don't need encoders really. Not necessarily. Moving on. Encoders again. If you want, you can revise them on your own, but these are not. We're not going to focus on that. We already did multiplexer in the last slide, so not focusing on that. Now, what's a 1-bit multiplexer? You can have a look at this one. It's a 1 bit. It's giving you 1 bit. So this is a 1-bit multiplexer. You can give it several bits. You can add layers. That's how we'll get multiple bits. Okay. Speaking of multiple bits, now you have a 2-bit. You say, oh, I'm still getting 1 input. Yeah, but you'll notice I'm still getting 1 output. But notice the inputs. I'll show you again. Look at the inputs over here, A and B. But look at the inputs over here, A, B, C, D. Isn't that the work of 2 multiplexers, kinda? A, B, C, D together. So that's why it's a 2-bit multiplexer, okay? So at the end of the day, you still get a 1-bit answer, but you're actually working out 2 bits at once, and that's why it's called 2-bit multiplexer. You can even make 4 bits. Okay, not to mention, let's just read this out. Selects from 4 n bits. These are the n bits. Inputs for each ABCD replicate circuit on previous slide. We did that, same as decoder. This works like a decoder. Ripple adder, we did this. Has to speed up. Now you know already we'll have to break it out to half and then do this, as you can see over here. This is a good conditional sum adder version, which is, it's called conditional sum adder. That's not a version. It's a better n by 2 times faster than, you know, ripple adder. Conditional sum adder is n by 2 times faster than ripple adder. So where do you take 15 bits? Now you may say 15. Yeah, because it starts from 0. So 0 to 15 is 16 bits, okay? And same from here. 16 to 31 will give you 16 bits again. So this total makes you 32 bits. So you find S0 to S15 from this part, and then you find the rest from this. Oh, what the 16 to what 16? Why did I write this? Forget it. Anyways, so you did this part using mux, and then when you have these 2, just put them in a mux as A, B, and you will give a selector from this, and you will get the rest of the sum. So it's n by 2 times faster. You just did half out your work. We already did this. We even did a better one. So what is this? Many others have been proposed. Small, slow ripple, which is very small, but it is terribly slow. Conditional sum, it's okay, it's in the medium. Sum of products, we did that one, but it's huge because you need all these logic gates for that. Now, how can we make things efficient? Oh, we already know ALU, right? Now, why is this so efficient? It is so because it is taking speed, and also it's kind of like ripple adder, you see? It's kind of like ripple adder. And it's kind of like that conditional sum adder. We're doing work of both very quickly. So mux is the magic over here. First thing you need to remember, who's the hero over here? this muxes, they are doing the real deal, and we are smartly using the get and this guy, which is new, b invert, to reduce our work, and that's how we are making the operation faster. We are focusing on not only speed, because if speed was the only fact, then we would have went with sum of products or conditional summator, which was kind of balanced. But we are also looking for space, complexity, everything. So as long as it's complex, it doesn't matter if these two conditions are satisfied, and that's how ALU rocks. It satisfied both. Okay, so ALU has different versions. What you will have to remember that it will use that b invert to do sum or do subtraction. I'll show you ALU now. After this, I will show you my own artwork, like if you understand, that is. I hope you will understand the drawing. It's Hebrew. So you have this mux, I created that, and this mux S.O.P 01. You'll find this node in the CSE340 folder. This is a half adder. I showed you this one already. And here is cam scanner. He's promoting himself, so pay attention to that too, as if someone cares. And you have ripple adder, and you have this conditional sum adder. I have detailed them out so that you can understand them. And the final hero, the mux. And then we have ALU, which uses b inverse and double muxes, two muxes. So the primary difference between, I forgot to mention, that conditional sum adder and ALU is that conditional sum adder uses one mux as the ultimate in output, but ALU is smarter, so it will use the mux in B also to just why will I draw separate half? I can just do out the half work using a B mux. So half will be done in one circuit. Why will I create another whole new half, which I will do in conditional sum adder, right? So that's, if B inverse is equal to 0, we perform addition. If B inverse is 1, we perform subtraction, which is actually A plus B naught. Okay, and programmable logic array. If you guys don't disagree, I think this drawing is nice. I'm not praising myself, I'm just like, when did I draw this? It's actually the magic of cam scanner. Anyways, and finally CSE340. Speaking of nice, this is horrible. Anyways, this is register, something we will do in the next video, so let's just keep it here for now. What we learned today, guys, is combinational logics. So dealing with marks, ALU, PLA, these are important for your mid and also for your finals. So remember the terms PLA, conditional sum adder, ALU, half adders, and logic diagrams. You will be told to draw logic diagrams, believe me. So those are the things we need. And with that, let's end the first video. Happy surviving, guys.